Hi, everyone. My name is John Wamburu. I am a PhD student at the University of Massachusetts Amherst. Today, I'll be speaking to you about our work titled Towards Equity in Energy Efficiency Analysis. This is work that was done together with Emma Grazier, David Irwin, Christine Crago, and Prashant Shenoy, all from the University of Massachusetts Amherst. I will start by talking about the introduction and a bit of background for our work. The first observation that we make here is that the electric grid is currently undergoing a major transition from primarily using carbon-intensive energy sources to more carbon-free and renewable energy sources, such as solar and wind. Now, data-driven techniques that leverage energy usage data from the grid play a key role in this transition. For example, they're used to identify inefficient homes in buildings and target them for improvement so that we can gain the highest carbon reduction by transitioning these buildings to renewable energy. However, most of these techniques do not focus on equity, and that will be the main focus of our work. So what do we mean when we say equity? In the broader energy transition, research has shown that the burden and benefits of energy transition are shared disproportionately. For example, in the case of wind turbines, wind turbines are mostly installed in rural areas, and one of the burdens that comes with that is noise from the rotating turbines. However, the benefits of the renewable energy from this wind sources are mostly accrued to urban dwellers. And that shows a disproportionate share of the burden and benefits across different demographics. In the case of energy efficiency analysis, research has shown that demographic factors such as household income affect the energy usage. For example, heating and cooling intensities are heavily influenced by the household income because they are directly correlated with the amount of money that will be spent on the bill. And therefore, analyses that seek to identify efficient or inefficient homes must consider such factors to come up with equitable recommendations for transition. This brings us to our research question. So given the background that we just went over, we asked the question, what biases exist in data-driven and machine learning energy efficiency analysis techniques, and to which degree are such biases present? To answer this question, we perform a case study on one energy efficiency analysis technique called WhatHome. And WhatHome identifies inefficient homes from a group of homes and the underlying faults for these inefficiencies. It uses a building energy model that is primarily based on the outside temperature, and it analyzes the heating and cooling intensities and uses outlier selection to identify inefficient homes from a group. This is the energy model that is learned by WhatHome, and you can see that there exists a temperature T heat below which there is need to heat the building, and the intensity of heating is characterized by the slope gamma heat. There exists another temperature T cool above which there is need to cool the building. The intensity of cooling is characterized by the slope gamma cool, and there exists a base energy baseline, which represents energy usage by home appliances, which is not affected by the rise or drop in temperature. With this technique, we ask the question, is WhatHome equitable in its recommendations when doing energy efficiency analysis? To answer that question, we leverage three main data sets. The first one is energy usage data from a small city in the North New England region of the United States that consists of more than 6,000 homes. The data type includes both electric and gas usage recording, and electric data is recorded every 5 minutes, while gas data is recorded every hour. And this data is from the year 2019. We also collect demographic data. The unit of data is the census block, And the key data points that we're interested in the demographic data is household income, the value of the house, and the size of the house. And we collect this data for the year 2019 as well. And finally, we also collect weather data for the same time period. And our main area of focus here is the temperature. We apply Watt Home to all the homes in our data set. And here are some resulting energy models that were learned. This first sample is showing a home with a moderate heating slope, but a rather steep cooling slope. So in the analysis, this house would probably be picked as having a cooling inefficiency because the cooling slope is rather steep when compared to other houses in the cohort. Here's another home that shows a moderate heating and cooling slope as well. And finally, here is a different home profile that shows a moderate heating slope and a non-existent cooling slope, which would signify the lack of an AC unit in the house. Now we apply Watt Home and select the top 10% of homes with the highest cooling and heating slopes. We then combine this with our demographic data and analyze the distribution of the income in the top 10% of homes in each of these categories. And here are some of the resulting analysis. So the first one shows that we observe that buildings with the lowest cooling slope, which would indicate that Watt Home would select this as being the most efficient homes, are predominantly low-income households. And this could potentially be a biased observation because it could mean that these houses probably do not have an AC unit and they are also inefficient. Their building envelope is inefficient, but they either lack an AC unit or the AC unit is not used as much as it would be in higher income households. And therefore, an analysis that would be looking at the most efficient or the most inefficient homes should take this into consideration to avoid this kind of bias. At the same time, we look at the distribution of house value in the homes with the highest heating slopes, highest heating slope in the data set. And again, here we find that buildings with the highest cooling slope are mostly high value homes. This could also, again, be a biased observation because this could represent homes that are wasteful or homes that are able to run their bill for longer periods of time. This is compared to the smaller number of homes that have been identifying as not having inefficiencies in the lower income, in the lower house value region. And this would potentially mean that these houses would not be selected as being inefficient, while in fact they may be inefficient. And if, for example, a subsidy was being offered for transitioning homes that are inefficient to more efficient energy, these homes would be left out, and that would probably be a biased result because these factors were not considered. With these two observations, this brings me to our conclusions. The first conclusion we make here is that a purely technical analysis in energy efficiency is not enough, and it might be inequitable. As we've seen, it might be affected by demographic factors such as the level of income and the house value. And therefore, we propose that equity should be considered as a key design goal for such techniques from the onset to ensure an equitable energy transition. Thanks for listening. If you would like to learn more about the work at our lab, you can do so by going to our lab home link. And if you have any questions regarding this work, you can contact me. Here's my email. Thanks again for listening.